The velocity of a wave is dependent upon the medium that a wave travels through. Now that might seem a little weird to you. You might think if I put more energy into a wave that its speed should go up, but that's actually not the case. Whenever you put more energy into a wave, into a mechanical wave, its amplitude goes up. Remember that from last video here. It's only dependent upon the matter that it travels through. Some common velocities that you'll find here are going to be sound. In standard air, about normal room temperature is somewhere around 340 meters per second. Light in a vacuum is constant, generally represented by the lowercase c. It's 3 times 10 to the 8th meters per second, 300 million meters per second, quite fast. Sometimes we use light years to represent distance, how far light would travel in a year. Velocity, here's the velocity of light times time, being 1 year. Get the years all the way down to seconds, right? So that's another way to represent distance that we're going to end up using sometime later on. But velocity of light, 3 times 10 to the 8th meters per second. Now, sound varies a lot more than light's velocity. But whenever you enter in new mediums, every single wave changes velocities. And the equation you're going to use to calculate that is velocity equals wavelength here times frequency. Velocity equals wavelength times frequency. Now, here's the weird part that I need to mention to you. Velocity only depends upon the medium the wave passes through. It does not depend upon the wavelength, and it does not depend upon the frequency, because those two things are being used to calculate it, but they are not being used to determine the velocity. Let's say a water wave, if we gave a water wave a higher wavelength, a bigger wavelength, so wavelength went up, then frequency would go down. In other words, the waves would get further apart, and they wouldn't occur as often to give you the exact same velocity, and vice versa. If we made frequency go up, we put more waves in there per second, the wavelength would go down, they're going to be closer together, which would give you the exact same velocity there. So velocity of a wave, wavelength times frequency, but please understand the velocity is only dependent upon the medium. You actually have to change the stuff the wave's traveling through to change the velocity. Another thought for you about graphs here, because you will have to use graphs to determine velocity. Remember, on a displacement time graph, the distance between two identical points, for example, crest to crest, is the period. And on a displacement distance graph, the distance between two identical points, for example, crest to crest, is the wavelength. Using two graphs that represent the exact same wave can allow you to calculate the velocity, because period, remember, 1 divided by the period equals the frequency. So if you do 1 divided by the distance in a displacement time graph, you get the frequency, you get the wavelength from the displacement distance graph. That allows you very simply to plug in over here to your velocity equals wavelength times frequency equation. Whenever we're just solving problems that only deal with velocity of a wave, they're very plug-chug kind of problems. For example, here a dolphin actually uses a form of sonar. It emits sound waves that are actually too high-pitched for us to hear. The human ear can't get up to 40 kilohertz in frequency. We can't hear that range. But they emit sound waves, and it bounces back, and they use basically a Doppler effect, a radar, if you will, just using sound wave sonar, to determine where their world is around them besides just their eyes. You can blindfold them, it does not matter. So to determine the world around them, determine how fast things around them are moving, which direction they're moving, so forth, so on. So here we want to know the velocity of sound and water. So velocity equals wavelength times frequency. We're looking for V. We're told our wavelength is 35 millimeters, or 35 times 10 to the negative third. And we're told our frequency is 40 kilohertz. And hertz is the base unit, so 40 times 10 to the positive third. And whenever you plug that into your calculator, you get the velocity of sound in water is somewhere around 1,400 meters per second. Now I'm going to come back and I'm going to do a demo in class that tries to demonstrate what occurs to the velocity of a mechanical wave in a medium. But basically, as the density goes up in a medium, there are other factors in this, but as the density of a medium goes up, the velocity of the wave goes up. Water is much more dense than air, so sound travels faster through water, 1,400 meters per second, than it does through air, about 340 meters per second. Another question, light from a dying star that reaches Earth has a wavelength of 680, be careful here, nanometers. What frequency of light is being received from the star? Note that it did not state the velocity. That's because the velocity of light every single time in a vacuum, and we take that also to be in air, is 3 times 10 to the 8th meters per second. You already know the velocity of light. So V equals lambda F. So our velocity of light, 3 times 10 to the 8th meters per second, equals our wavelength, 680 nanometers, and nano means times 10 to the negative 9th. Not worrying about putting that in proper scientific notation here in the problem because our calculator will do that for you. Divide both sides by your, that should be F, frequency. Divide both sides by your wavelength, 680 times 10 to the negative 9th, and you come out what frequency of light that is supposed to be. Comes out to be 4.4 times 10 to the 14th hertz is the frequency of light. And the entire trick with any problem that involves light is just remembering the velocity, 3 times 10 to the 8th meters per second. All right, the last question that I want to do for this is using graphs. So I have 2 graphs here showing the identical same wave. It's just one graph is showing the displacement time, and the other is showing displacement distance traveled by the graph, or by the wave, excuse me. So I know from these I can get my period and my wavelength to then plug into my equation, V equals lambda F, right? And 1 over the period gives me my frequency. So I need to let's start out trying to figure out my frequency. This area right here is one half of a period. Okay, 1/2 of a period. It's half of a full rotation of a wave. If you want to see that as more a full rotation of a wave, this distance right here would be the entire period because it starts here, goes up, and let's grab our laser pointer, goes up, goes down, comes right back to where it started again, going back up in that direction. So there's one entire period. So our period, T, according to this, is going to be 0.50 seconds. Our wavelength here, distance from, we can do it from, let's take it from here all the way over to here, start to finish. Our wavelength is going to be 1.0 meters, 1.0 meters. To translate our period into frequency, remember 1 over T equals F, so 1 over 0.5, F is going to come out to be 2 hertz. So velocity equals wavelength times frequency. Velocity equals 1.0 times our frequency of 2.0, because I had 2 sig figs in each of these graphs. Both of those are in base units of meters and hertz. Make sure you check out the units on the graphs, and I come out with a velocity of 2.0 meters per second. The most confusing part about these problems with graphs is probably just reading the graph to actually pick out an entire rotation of a wave. Just make sure that the wave goes through an entire rotation, goes up, goes down, and comes back, or if it's in 180 phase difference, right, goes down, comes up, and goes back. So it needs to do an entire rotation. That's why you can also do crest to crest. From here it goes down and comes all the way back up to the exact same spot. So just make sure you pick an entire rotation of a wave to give you your either period or your wavelength, depending upon which graph you're looking at.